Hello students and good evening. Welcome back to my channel. Today in this video we'll be discussing questions which were asked on 27th of January 2024 JEE mains. Okay. The topic of discussion is moving charges and magnetism. We'll be discussing questions based on moving charges and magnetism. So without wasting time, let us continue this. So here you can see a proton moving with a constant velocity passes through a region of space without any change in its velocity if E and B represent the electric magnetic fields respectively in the region of space has. So we have to explore various possibilities when this condition would be encountered. It's clearly given that it passes with a constant velocity, okay, through a region of space without any change. So if and all. If E and B represent the electric and magnetic field, then now as you know, Lorentz force is given by the electric force plus the magnetic force. This is the Lorentz force. So if it passes with constant velocity, that means acceleration is zero. So if acceleration is zero, force has to be zero. So what are the various possibilities? If E is zero and B is zero, yes, of course, E could be 0, B could be 0. There is no electric field, no magnetic field. So, no question of any force. So, the proton would move with constant velocity. Then, coming to the second possibility, E is 0, B not equal to 0. Yes, it could be possible, students, because if E is 0, there is no electric field. Okay. But, in spite of B being present, it is possible that V cross B is 0. When it would happen? When V is parallel or V is anti-parallel to B. In either cases, the cross product will be 0. If theta is 0 or if theta is 180 degree, in either case cross product will be 0. So there won't be any magnetic force. Yes, this is also possible. Then coming to this, if E is not equal to 0, then certainly electric force will act. And of course, if B is 0, no magnetic force, in the presence of only electric field, so it will experience force and hence it will get accelerated. And because of acceleration, velocity will change. So this is not possible, students. Okay. Then coming to this, E not equal to 0, B not equal to 0. Yes, it is possible. For example, suppose the force due to electric field is exactly equal and opposite to the force due to magnetic field. Then it's quite possible that in spite of both fields being present, the particle will move undeflected. It will go undeviated. So this is also possible. So correct options are A, B and D. So I'll go with the third option, A, B and D. Then moving on to the next question, students. A rectangular loop of length 2.5 meter and width is placed at 60 degree to a magnetic field of 4 Tesla. The loop is removed from the field in this. Now student, one thing I would like to mention that all these questions have been picked from internet and they are all memory based. Okay, and of course memory based may not be 100% authentic. Okay, but of course nevertheless we definitely get a good idea, pretty good idea regarding the type of questions they are asking. Maybe memory based problems may not have the exact values, but we definitely get a clear-cut idea of the nature of the problems, the type of the numericals they are asking. So it doesn't matter even if numerical value will change. So what I mean to say is that there could be slight, confusion as to what is the scenario, because students who have memorized and they are able to reproduce, they may not be able to reproduce 100% exactly what was asked. So slight changes could be there here and there. Doesn't matter. So the length and breadth of the loop is given and it's placed at 60 degree to the magnetic field. So it's not very clear whether the plane is making 60 degree or the area vector is making 60 degree. Anyway, we'll assume that the area vector is making 60 degree. Okay, students. Of course, only one turn is there, so no need to draw any turn. So this is the area vector. So area is equal to length into breadth, so 5 meters square. It makes an angle 60 degree with the magnetic field. Magnetic field is 4 Tesla. So the average EMF induced in the loop during this time. So it is removed. Now as you know, according to Faraday's law of electromagnetic induction, the average EMF induced is equal to the average rate of change of magnetic flux. So the average rate of change of magnetic flux means what? Change in flux will be final minus initial. So finally it has been removed out of the magnetic field. So there is no final flux. Okay students, only there is initial flux. So initial flux is B A cos theta. So let us substitute the values here. So we have minus, the time interval is 10 seconds. So I'll have minus 1 by minus 1 by 10 second into minus B. B is how much? B is 4 Tesla, area is 5 meters square, cos 60 is half. So exactly we are getting plus 1 volt. Okay, 20 and 20 gets cancelled. Right, moving on to the next question. Question number 43. A current of this much microampere deflects the coil of a moving coil galvanometer through 60 degrees. The current to cause deflection through pi by 10 radian. So we'll do one thing students. I'll write 60 degree as pi by 3 radian. As you know, in case of a moving coil galvanometer, current is proportional to theta. Isn't it? Current is proportional to theta. So therefore I2 by I1 is equal to theta 2 by theta 1. So what is theta 2? Theta 2, the new angle of deflection is pi by 10, whereas the initial angle of deflection of the coil was pi by 3. So 3 by 10. So I2 will be I1 into 3 by 10. So I1 is how much? 200 microampere. So into 3 by 10. 0, 0 gets cancelled. You have 60 microampere. So this is the correct answer students, 60 microampere. Then moving on to the next question, question 44. Two long straight wires carry equal currents in opposite directions. As you can see, the figure is given. The separation between the wires is 5.0 cm. The magnitude of the magnetic field at point P midway between the wires is this much microtesla. Now, due to wire 1 and due to wire 2, by symmetry they will be numerically same and also direction wise same. Due to this wire it is along the inward normal, and due to this wire also it is along the inward normal. So the net magnetic field will be twice of magnetic field due to any one wire. Now field due to an infinitely long wire is, you know, mu 0 into 2I by 4 pi a, where a is the distance. So here mu 0 by 4 pi is 10 to the power minus 7, twice current is 10 ampere, and separation is 5 by 2 centimeters to be converted into meters. So this much Tesla should be the full and final answer. Okay students? Right. So here we can see that it is 8 by 5 into, this is 100 into 10 to the power minus 6 Tesla, because this will be 10 to the power minus 6. Here it is 1. This 10 power minus 2 goes up, becomes plus 2. So 5 into 20. So we have 160 microtesla. So 160 is the answer, because we have to obtain the answer in microtesla. Okay students, coming on to the next question. You can see two coils have mutual inductance this much. The current changes in the first coil according to relation this, the maximum value of EMF in the second coil. So here the first coil is the primary, second coil is the secondary coil. Right. So EMF induced in the secondary coil will be mutual inductance multiplied by rate of change of current in the primary. So here mutual inductance is 2 millihenry. So I write this as 2 into 10 power minus 3 Henry. And the current is this. So we have d by dt of I naught is how much? 5. And omega is 50 pi. So this we have to differentiate with respect to time. So we have 2 into 10 power minus 3 into 5 is a constant, will come out, multiplied by 50 pi into cos of 50 pi t. Okay students, we have to get the maximum value. So maximum value will be when the value of cos is maximum, and that maximum value of cos is 1. This will be 1, this part. So in that case, the maximum value of EMF will be 2 into 5, 10. So this will be 50 pi into 10 power minus 2. Okay students, in other words, this is 50 pi, 10 power minus 2 is 100. So it is pi by 2. So alpha is 2. This is 10 power minus 2. 10 power minus 2, 50 pi. Alright students, moving on to the next question. The magnetic field at the center of a wire loop formed by two semicircular wires of radius this much and this much carrying a current 4 ampere as per the figure given below is this much Tesla, the value of alpha is. Now as you can see students, we have altogether 4 wires. You can number this as wire 1, this is wire 2, this straight part as wire 3 and this semicircular part as wire 4. As you can see, the magnetic field due to wire 1 and wire 3 will be 0 here because the point happens to lie on the axis of these wires. As you know students, magnetic field exactly on the axis of a cylindrical wire is 0. So we should be concerned only with the magnetic field due to these two semicircular wires, that is wire 2 and wire 4. So magnetic field due to a semicircular wire will be half into magnetic field due to a complete coil, and magnetic field due to a complete coil is mu 0 I by 2R. This is the formula students. And you can see due to wire 3 it will be along the inward normal. If you apply this, if you curl your fingers other than the thumb of your right hand in the sense of current, thumb shows you the direction of magnetic field at the center or along the axis. Similarly, due to wire 4 also you have the same. So therefore the net magnetic field will be the sum of the magnetic fields due to each. So we have B net B is equal to B2 plus B3. So this will be half times B2 is mu 0 I by 2 into R1 and B3 is B4 is mu 0 I by 2 R2. So we have mu 0 can be written as 4 pi into 10 to the power minus 7 by this 4 can be taken common, I can also be taken common, I is also 4. We have 1 by 2 pi plus 1 by 4 pi. Sorry. So this 4 gets cancelled here. Okay. Pi 2 gets cancelled. So we are left with 4 into 10 power minus 7 here. 1 by 2 plus 1 by 3 is 1 by 4. So 4 gets cancelled. We are left with 3 into 10 power minus 7 Tesla. So alpha is 3 here. Okay students, moving on to the next question. Yes, all the questions are over. That's all students in this video. Thank you so much for watching my channel.